Okay, so we're still doing Ginsburg-Landau. And eventually, this is a theory about writing the free energy as A minus H m plus B m squared plus C m to the fourth. And we explained why they do this expansion around the critical point. So all this work in T very near to the critical temperature. And we have found that the transition from one solution to three solutions occurs when B crosses to 0. Okay, so there is, if B is greater than 0, there is only one solution, m equals to 0. And when B is smaller than 0, there are three solutions. So m equals to 0, or m equals to plus minus square root of minus B divided by 2C. So in this theory, we do see that there is a transition from something that is only stable when m equals 0, so the order parameter or the magnetization has to be 0. But when we cross this specific point, when B becomes negative, there is a additional possible solutions where order occurs. So order here is a non-zero value of m. What exactly happens when this transition occurs? So what happens when it goes from B being positive towards B being negative? Okay. So we have seen already in this Ising model, okay, we have seen this Ising model that this is exactly this point of critical phase transition. So basically we can say that when B is positive, this is T larger than Tc. And when T is negative, this is when T is smaller than Tc. So Tc is defined, okay, T is defined with the situation when B equals to 0. Now, so this is the exact transition, and as we see it, we can also find it out from this behavior of the derivatives of f. If you remember, we have taken several derivatives of f's. This is what led to this solution. Great, but this is very nice, but we knew it already. How we can establish something additional using this expansion and using this assumption that we are in the vicinity of this critical temperature, but something additional to what we have already seen in the Ising model. Okay. So first of all, we need to describe our temperature. So we know that we are working in the vicinity of Tc. So we define a reduced temperature. What is a reduced temperature? We call it T, which is basically T minus Tc divided by Tc. Okay. So it's a unitless quantity, okay? And we know that we are working in the regime when this reduced temperature is 0, because we are working in the regime when T is very close to Tc. All those notions about universality and that many different systems behave exactly in the same fashion comes from the fact that we assume that in this region when T close to Tc, we indeed can expand our free energy in this form. Okay. So all this Ginsburg-Landau theory works when T is around 0. It's close to 0. We cannot have extremely large or extremely small T. Everything is in this expansion, which is basically, as you see it here, is a power series expansion, only occurs when T is close to 0. Okay. So how is this related to this transition that we observe of appearance of two additional solutions when B equals 0? Okay. So the question is how B depends on temperature, basically, or if you're looking, instead of temperature, we're looking on T, the reduced temperature, we ask the question how B behaves as a function of T. So what we know that B at 0, when this temperature, the reduced temperature equals 0, we know that we are exactly at the transition. Why? Because exactly when B equals 0, we have two additional solutions that pop out of nowhere. Okay. So those are the two solutions. So we know that B equals 0, it is exactly or 0. Okay. Now, the next question, and this is again the assumption of Ginzburg and Landau, if T is small, okay, so exactly at 0, it is 0. But when T is small, when the reduced temperature is small, what we can assume about the behavior of this exponent of this coefficient B. Okay? So they assume the following. Let's assume that B, as a function of T, it cannot be a constant plus something multiplied by T, because we know that at B of 0 equals 0. So we simply say that B of T is proportional, or it goes like as B multiplied by T when B is constant. Okay, basically we erase this, and we observe that B of T, and this is the assumption, scales like B multiplied by T, where this is some constant. Now you can say, well, Stas, it's not exactly true. Maybe it's B multiplied by T to some power. Right. But this is part of their assumptions, right? The assumptions was, well, we include here some symmetries, and we assume that the behavior of this coefficient, which stands here, and this term is here only due to symmetries, is analytic in the vicinity of T equals 0, and they assume that this goes as B to the first power. It could be B to the second power maybe, or to some fractional power. This is not part of the assumptions of the Ginzburg-Landau. Why? The answer is, why not? Okay, okay, so the moment that we have this, the theory is basically, it's basically pretty much finalized. We can obtain all the other behaviors, or all the different behaviors of the system, any system, based on what we already saw, and then we assume that B in the vicinity of the critical temperature have a linear dependence on the temperature, A is some constant, and actually about this term we don't really care. We will care about it only when we have H, which is not 0. Okay. Now, what makes, when I started to tell you, well, there is some universality, and that Ginzburg and Landau were looking for this universality, what I mean by universality is the following. In many different systems, well, it's really hard to obtain what is the free energy, right? I don't really know what the free energy is. I have a chunk of metal or of some material, and well, how do I know what the free energy of this material? Maybe you can calculate in some simple model what's the free energy of this model. But for a given material, this is not something that I can do. What I can do is to ask the following question. In many materials, if I plot M as a function of T, okay, we already seen it, the same behavior appears. So it's 0 up to some critical Tc, and then it rises up. Either it goes up or it goes down. Right? So the question is, in the vicinity of the critical temperature, how my magnetic moment depends on the temperature. So I know that it goes like 0 over here. This is the paramagnetic state. This is very simple. But what happens in this ferromagnetic region? And what they found in many experiments, so MT goes as T to some power alpha, okay? And this alpha was the same for many different materials. So when I'm speaking about universality, the universality is that it's not about that this critical temperature is the same for many different materials. No, the critical temperature is going to be different from when we look on one material or the other. But what's going to be exactly the same in many, many materials is this alpha over here. Okay?
It's going to be the same alpha? Or?
It's going to be almost the same alpha. So there are classes, but all the different materials in one class are going to have exactly the same alpha. And this alpha is going to be dependent if I'm looking on two-dimensional system or three-dimensional system. So it's basically defined by the symmetries and the geometry of the system, or dimensionality, but not all the microscopical properties. This is why it was called universal critical exponent. So universality appearance of critical, of similar critical exponents. So for example, if I have this form of my free energy, first of all, what I know from this free energy, I know that when my free energy looks like this, there is always going to be a second order phase transition, this continuous transition of M. This what that we'll see, that B becomes 0, and then out of nowhere we have two additional solutions. Okay? Now you can say, but what's about alpha? So what Ginzburg-Landau theory predicts about alphas? What can we say about alpha? This we can obtain from this BT over here, right?
M זה נקודת החיתוך בין הציר Y
M?
כן, M הזה ששנת MT.
What is MT?
כן, כן.
No, this is this function over here.
Okay.
It is 0 when the temperature is above Tc, and it is something which is non-zero when the temperature is below Tc. So what do we know about M? M as a function of T. Okay? We do know that it is a square root of minus B divided by 2C. C is some constant, okay? B, I know that is when T is around 0, right? We know that this is a square root of minus T multiplied by B multiplied by 2C. Okay? So let's write down what is T, if I remember correctly. So this is minus B divided by 2C, and here we have T minus TC divided by TC. Okay? So I can write it down as a square root of B divided by 2C TC, and here I have TC minus T to the 1/2. So the Ginzburg-Landau theory tells me the following thing. It tells me that if those are the only symmetries that I have in the system, and I can have very different behaviors in the system. It can be a magnetic system or some other system where I'm looking on order-disorder transition. And near this transition, I can indeed expand my free energy in this power series, very simple power series. There is going to be, for all the different systems, they're going to have different critical temperatures. Okay? Because B is, well, exactly how it goes to 0, it's a different way. It's a different question. But what happens when I'm looking in the vicinity of this phase transition? When I'm zooming in on this region and I ask how M grows as a function of the temperature. And for those many systems, it's going to be proportional to the Tc minus T, and this critical exponent is going to be 1/2. Okay? So this is the first critical exponent, and that we can easily obtain from the Ginzburg-Landau theory. Now, is this the right exponent? So if I'm going to look on Ising model, true Ising model, in 2 dimensions or the Ising model in 3 dimensions. Remember, what we have solved, we have approximated Ising model by using mean field approximation. Okay. So for Ising model, this alpha, okay, if d equals 2, this alpha equals to 1/8. If d equals 3, so nobody really knows how to solve it, so Ising model can be solved in 2 dimensions, and only for nearest neighbors, right? I cannot solve when every spin affects any other spin, only when I'm affecting spins that are in my neighborhood. So only then the Ising model can be solved, and we obtain this is alpha is 1/8. When d equals 3, we can solve it by a computer simulation, so it's numerical solution, and this alpha is 0.327 something. No, you cannot solve it. There is no solution. Okay, so it's an open problem for the Lux. Onsager solved it in 1944, and beforehand for 20 years they tried to solve it. Nobody could. So Onsager solved it. The proof is like 45 pages long. Very, very tough. Nobody really knows how to solve the Ising model for d equals 3. The mean field that I presented to you, well, it's easy. Well, easy, right? But we made some assumptions. But for d equals 4 and d equals 5, and don't ask me what exactly is the system that have 4 dimensions or 5 dimensions or 6 dimensions, okay? Alpha equals 1/2 exactly. Okay, so the mean field approximation is good, at least for this system, when the dimensionality is good enough. Okay. It sounds a little bogus, but it only don't. Sorry.
What is bogus?
Crazy.
Crazy. Yeah. But why is that? Why is it? So first of all, it's an approximation that we use, and it indeed provides to us a solution that there is indeed and why there could be a second order phase transition. And we can understand what is the physics behind this phase transition. It's not really exact because we neglected correlations over there. Remember, we had the small parts, but I said, well, those are small. Let's try and neglect them. I haven't told you why they're small, how they're small, and they are not really small when we're looking on d equals 2 and d equals 3. Okay, they are really important and they modify, but the alpha is not really far away. Okay. But in general, this physics stays the same. You do have critical exponents. We are a little bit off, but we still can understand why they are there. Okay? So if I would like to take Ginzburg-Landau theory, what it means is I have to perform 2 modifications. I have to include maybe additional symmetries, so this expansion maybe is not so correct, because if this expansion of the free energy was correct, I should get here alpha equals exactly 1/5. So what we do know is that the expansion is different, but if you will provide to me the expansion, I can return or basically retract all my steps and actually obtain the correct alpha. So the theory is correct, is that the assumptions of how exactly the expansion looks, there we made some mistakes. Okay? And we don't really know how to include those ahead to those correlations or those behaviors. There are other additional critical exponents. Right? So by learning about those critical exponents, you can understand something about what happens to the system. Okay, so additional exponent that was really interesting is...
When you mean critical exponents, you mean the alpha?
Exactly. So not what I mean is this alpha over here. This is called a critical exponent. Okay. So there are numbers of critical exponents, and it is all related to what an experimentalist can measure. Right? He can measure, he or she, they can measure the growth of the magnetic moment. This is something that is measurable experimentally. And so in different experiments, the critical point is going to be different. But this alpha is going to be very, 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 very close to 1/2 in extremely many cases. Extremely many cases. And what it means is that all those different cases are described by this expansion of the free energy. Okay? So the universality comes from the expansion. Near critical point, many different systems have exactly the same expansion of the free energy. And this expansion, this is what dictates the appearance of 1/2 or a different value. Okay. This basically means that many different systems, when we are close to this criticality, and this is a true critical point I call TC, a critical point, when we are close to this criticality, many different systems behave effectively the same. Okay? So this is what interesting, this is what really was surprising, and this is what really people needed to understand or appreciate. Right? So we look on different systems, and they look to us different, and they have some different properties. But when we push all of them towards this one singular point over here, all of them start to behave exactly in the same fashion. And this, how exactly it's going to behave, it's provided by how you can expand the free energy here. Okay? And we solve only one simple example, right? We can complicate this expansion as much as we want. For us, this is the simplest possible example, and this is why we solve it. And this is how we obtain those critical exponents over here.
איך ידענו אבל ש-B שווה למינוס בטא T פה?
So how we knew that this, so why B is this guy? So we solved it before.
לא, אני שואל על T, אני שואל על B להחליף את זה בבטא T. זה מה שאני שואל.
This is we've done in the beginning of this class. It's written over there. Yes.
התיאור הזה של F הוא רק בסביבות T קריטי?
So yes, so this expansion is capable of doing this only in the vicinity of critical T. So you can actually go and say, well, I can expand my free energy anywhere, right? But the claim is more bold. The claim is, because I observe exactly the same critical exponents, and all those different critical exponents are defined by the same expansion, by the expansion of the free energy, all those different systems have exactly the same expansion. Because they have exactly the same critical exponents. So what I can observe this 1/2 or 1/8 in different systems. And then I go backwards and I say, if it was 1/2, it means that the expansion of the free energy was of this form. And I do this for system number 1, for system number 2, system number 3, etc., etc. And then I start to appreciate that all the different systems in the vicinity of the critical point have exactly the same expansion of the free energy. This is something universal, global, that near critical to criticality, all the different systems behave in the same fashion. Let's see what other critical exponents are there.
That's the expression for M depending on T is only true for when H equals to 0?
Yes, so if it's not going to be 0, you're going to obtain something different. Right? So you remember, if H it's not equals to 0, there is no critical transition, it is smooth. Good. How you can obtain it? You work out through this derivative of f that I've showed you on Sunday. Okay, so to your question, how M behaves with H when the critical temperature is exactly Tc. Okay? So for T equals to Tc, so I set my system to the critical temperature. Then I have, so what knobs an experimentalist have for the system? The experimentalist can modify the temperature of the system, and he can modify the external field, H. Okay? So beforehand, I set H to 0, and I looked, when I modify my temperature, what's happening over here. Now we can look, as the other question, let's set the temperature to the critical temperature, and see if I modify a little bit my external field, how this magnetic moment is going to change, how my order parameter is going to be modified. Okay, so what do I know? Okay, so we already know that we have this equation, hm plus d m squared plus c m to the fourth. And we use this equation, df to dm equals 0, in our expansion or exploration of the saddle points of this equation, right? So we look on this, right? So what we obtain that minus h plus 2bm plus 4cm to the third equals 0. So basically we have 2bm plus 4cm to the third equals 2h. Now, exactly at t equals to tc, what is b? It's 0. C is some constant, so we have 4cm to the third equals h. So m goes like 1 over 4c to the third power h to the 1 over delta, where delta is 3. Okay. So if I'm looking, or if I want to check if my theory is correct, what do? I look for the critical temperature. I set the system at the critical temperature, and then I start to modify my external field. When I modify my external field, I see that m 1 over delta. And that I have almost the same delta for many different systems. Different systems, they can have different critical temperature, they can have different shape, they can have many different values, other values. But at the vicinity of this critical point, as a function of the external field, they all behave exactly in the same fashion. Again, delta is this additional critical exponent that we observe. So we already had alpha, we have delta. And we can look on another one, which is also important, is what happens to the derivative of m with respect to this external field. Okay? When I'm looking at h equals 0. So this is susceptibility heat. Right? You learn about susceptibility when you learn about electromagnetism. Right? So you look on the system, so you look on the response of the system to the application of external electric or magnetic field when this field is 0. Okay. So how we observe this, what's the behavior of this guy? So we can also start from this equation over here.
But what is the phase transition for the delta?
What do you mean? What the predictions?
What is the phase transition?
No. So there are no other phase transitions. We found it already. There is only one phase transition. But in the vicinity of this phase transition, something interesting happens.
But what's so interesting about the delta?
Well, very interesting. People published extremely many papers about this. But to be exact, what is interesting? What is interesting that you take this marker, all right, and you bring it to a critical temperature, okay, and you apply an external field, and you measure this delta for this external field, right, and you obtain 3. Then you take this cup, right, which is different from this marker. You agree with me? Right. You take this cup, you bring it. If there is a critical point, all right, you apply an external field, you measure how this general magnetic moment behaves with the external field, you measure it's going to power 1 over delta, and it's the same delta. It's exactly the same delta for completely or apparently 2 different systems. This is what's interesting. You take different systems which behave very differently for general range of temperatures. You bring them those 2 systems to this critical point, and they start to behave exactly the same. Right? That's what's interesting here. Yes. If they can become a ferromagnet, they start to behave exactly in the same fashion. That's the so so if you push it a little bit farther from the critical point, they will behave differently. If you go into this region, they will behave differently. If you stuck it in this point, critical point over here, this is why it's called critical, they behave exactly in the same fashion. That's the interesting part of it. So think about it as a puzzle. People measure different the behavior of magnetism for different objects, and they observe exactly the same behavior. So if they measure it for high enough temperatures, the different objects behave differently. If you measure it for low enough energies, the different objects behave differently. But when you measure exactly at one singular point, they all behave exactly in the same fashion. That was a riddle, right? And the riddle is explained by this happens due to the fact that in the vicinity of this critical point, the free energy of many systems is exactly the same, or at least its expansion. Yes. No. So the this is a critical point to understand about the critical temperature. It's different. Everything is different. The forces between the particles are different. Everything, if you think about the microscopical properties, they are completely different. The critical temperature is also not exactly the same. It's completely different. It can scale by not hundreds, but tens of Celsius. But the behavior, what I mean by the behavior, is the appearance of those exponents over here. They were exactly the same. Think about as what I'm telling you is the following. Right? You're used to what? They're used to any two objects attract each other with a force which is proportional to what? To the distance between the forces to the power -2. Right? Why is that? Why this marker and that marker won't attract each other to some other with some other force? Right? We believe that there is a gravitational law that applies everywhere in our universe. Why is that? Right? You ever ask yourself this question? Why this law of gravitation is not different on Mars? Right? There is some sort of universality that describes to you that something about how the fabric of our universe is formed. Exactly this happens over here. You take two completely objects, right, that should behave somehow differently. Why not? And they indeed behave differently unless you push them to the limit of this critical point, and then suddenly everything looks the same. It tells you something about how the nature is structured. That's why it's beautiful and that's why it's interesting. And the true solution, we won't learn about the true solution, but the true solution is called the normalization group. It was developed in '73 by Wilson and the ideas of Leo Kadanoff. And eventually this is one, there is not a lot of prizes in statistical mechanics, Nobel prizes, and there is not a lot of general prizes on theoretical physics. Usually they're coming on experimental physics. So this idea of how to understand this universality is actually brought very fast a Nobel Prize in physics. So we have a couple of minutes. I want to finish with the behavior of this susceptibility. Okay? Because this is the last exponent and it actually tells us a little bit more about what happens over here. What exactly happens over here? What? Susceptibility? Okay. It is. And it's going to be different here, and here, and here, and here, and here. But in this, exactly over here, it's going to be the same for many different materials. Okay? So the power, you will see in a second. You will see in a second. And the behavior of the susceptibility is actually why it's critical. All right. So, last 5 minutes. I promise. Okay, so how we obtain the susceptibility? Let's take this equation, okay, and take the derivative of this equation with respect to h of the left-hand side and the right-hand side. So we have d to dh of 2bm plus 4 C m to the third equals to d to the dh of h. Okay. So what we have on the left hand side? We have 2. B is only depends in this region when we're really close to the critical temperature. Remember, so all what I'm doing is applicable only here. Anywhere else, all those tricks do not work. All these assumptions do not work, but here somehow they do. Okay? So this is 2b dm to dh plus 12c m to the second power dm to dh equals 1. Now, what is dm to dh?
Susceptibility.
This is here, the susceptibility, right? So we have 2b of susceptibility plus 12c m to the second power of susceptibility equals 1. So susceptibility equals to 1 over 2b plus 12c m squared. Now, how m is behaving as a function of temperature? So m equals to what? Square root minus b divided by 2c, right? So it's proportional, we already know, to t minus tc to the second power, to the 1/2. So m squared is proportional to t minus tc to 1. Right? B, we already know that this is b multiplied by dt, which is equals to b of t minus tc divided by tc. So 2b plus 12c m to the second power, proportional to what? B goes to t minus tc, right? And m squared is also t to the minus tc. Okay, so all of this is proportional to t minus tc to the first power. So what we see is that x, we don't care about all the different coefficients that we have. Remember, because the only thing that it is interesting is what is the power of the exponent. What this looks like. So he goes as 1 divided by t minus tc to 1, which is t minus tc to minus 1. This is the susceptibility. So if we plot this susceptibility, this is T, this is T, and this is TC. Remember that I told you, well, this is a critical point, there is some sort of phase transition, but this is a smooth transition. What is critical about it? The critical is the response. The susceptibility is critical. Why? Because what we obtain that exactly at t equals to tc, the response becomes infinite. Okay? So if we plot this, the susceptibility is going to diverge to the left of the critical temperature and to the right of the critical temperature. Right? And this is what we observe in the critical phase transitions, that susceptibility is diverging. The response of the system to some external field is somehow diverging. And in many systems, they are diverging at the critical point, although the systems are different, and the law how they exactly diverge, okay, goes as t minus tc to the power of minus gamma. And this gamma is exactly the same. This is the third critical exponent. is exactly the same for, again, universally large class of systems. Okay. This is gamma. So we observed alpha, delta, and we also observed gamma. And for the susceptibility is the most important because it actually tells us what is critical about this. The critical is that the response becomes divergent. Okay, so what do I mean divergent? You shift it a little bit to the right and the response is not even proportional to the amount of force that you invested. Right? All of this is computed near h equals 0. You shift it a little bit and it explodes. So we're finishing up here. I have no time to describe you those ideas of our normalization group and how they really beautiful. Sorry about that. But I have finished at least the material that we that I teach every year, and hopefully you enjoyed yourself. Thanks. See you at the test.
סטס, אתה רוצה לספר לנו על הקורס שלך?
מה? בואי, יהיה כיף, אין מבחן.
אבל יש שיעורי בית.
יש שיעורי בית.
המון.
לא, לא.